Alright, so in this video lecture, let's apply our understanding in calculus into finding areas in polar coordinates. And so it is in the way how it, according to the title, then it's required that we must learn this video lesson, or we must watch this video lecture after you have already understood and studied about how to apply the fundamental theorem of calculus into finding a definite integral. Okay, or in short, just how to evaluate a definite integral using the fundamental theorem of calculus, the second part. So that's a required understanding before we can study this any further. And needless to say, anyone arriving at this video lesson should be able to, should have learned past how to operate with polar coordinates, should have learned past the understanding of what polar coordinates is, and how to sketch graphs on polar curves and all that. Okay, so in case you are not familiar with polar coordinates or graphing curves in polar coordinates, find my other video lessons on this topic about polar coordinates. Okay, all right. So now let's get started. And so allow me to introduce the idea before we can rush into doing the work right here. So primary goal right here, we are going to find the area in a curve that is represented in polar coordinates. But so now when anyone studying about polar coordinates, especially when you got into graphing a polar curve right here, then at least if it was my class, and I would always mention clearly that a curve is just a curve, being in Cartesian coordinates or being in polar coordinate, it's just a way of representing the curve like that. And so now we just have a curve. In the x and y system, we have a curve. Okay? And we have a curve. It could be an arc, it could be a bent curve or whatsoever. So now when we're here about finding the area bounded in this curve, now for anyone who already had some learning on how to find areas using calculus, then more likely you're going to be thinking about the area we're about to find is in a picture like that. Okay? Unfortunately, it is not. Area we're finding this in this way how I'm sketching the area. In this way how I'm sketching the area. This is the area, but in Cartesian coordinates, or another way of saying this is in rectangular coordinates. So that's not, so I have to be clear, this is not the area we're looking for. Yes, there's that same curve, but in Cartesian coordinates right here, then the area is going to look like that. We're gonna from a start to an end right here, left to the right. That's the primary thing with Cartesian coordinates. And so in Cartesian coordinates, we're going to shade the area between the curve and the x-axis, or one of the major axes, and then between from the left to the right or from bottom up right here. That's the idea about areas when it's in Cartesian coordinates or rectangular coordinates. Okay, but so that's not what we are focusing in this particular study. What we are doing here is we are looking for area bounded inside this curve, but in polar coordinates. So here's how it is in polar coordinates. And so sadly I have to erase this shading, because this area is not the area of that curve bounded inside of that curve here in polar coordinates. Alright, so the curve itself, that piece of arc, I'm leaving there the same. But allow me to erase the area, because that amount of area is not the area we're looking for. It's not the area in polar coordinates. So now I have to remind the idea of polar coordinates a little bit before we move on into finding area. But now this same curve, like I said earlier, at least for students learning in my class, I've always mentioned it clear, the same curve, the same physical curve can be written it can be expressed either in Cartesian coordinates or polar coordinates. So if you're expressing this curve in terms of polar coordinates, then every point on this curve, every point that we place on this curve is represented in terms of, first, how much radius that point is made with the origin. or the origin now in polar coordinates is referred to as the pole. Okay, so the pole is at 0, 0. Okay, but then any point on the curve or any point in the plane is represented in terms of how much radius it's made from the pole. So the pole is a different name for the origin, and so that point has radius r. Okay, and aside from how much radius, the point is also represented in terms of how much angle opening up from the positive x-axis, and that angle here we denotes that theta. Okay, and so and as a convention, positive direction is the counterclockwise direction, and the negative angle is the clockwise rotation of the angle. Okay, but so the angle is always referenced how much that is in respect to the positive x-axis. That's what the angle is. Okay, and so once again, that's how we represent any point. Okay, on that on any point on that curve, but using polar coordinates. So in polar coordinates, that's how we express a point. So in that way, when we apply that understanding into finding the area now, so the area in polar coordinates, how do we imagine that? How can we imagine that? So in polar coordinates, here's how I'm seeing. So if this was a curve in rectangular or Cartesian coordinates, then a curve like this, we would look at that curve from the left to the right. And as I said, if this was, the curve being represented in Cartesian coordinates, then the left here, this is the left endpoint, and this is the right endpoint. And we are finding the area from the left to the right. That's how the shading is. But now, remember, for when we're doing in polar coordinates, the curve here changes depending on where the angle opens up. And so opening of an angle is always from small to large in a positive direction, is always going to go like that, from small to large in a positive direction. So that means this is the left side here is not really the start of our curve, and the right side here is not really the end of our curve. The end of our curve or the start of our curve is wherever. So now I'm going to really erase this line right here. But let's think about, in this curve, if we're making a positive turn, because that's what the way it is. Positive turn is indicating from small to big and keep getting larger. And we are referencing ourselves to this positive x-axis right here. So as in terms of the positive turn, the positive rotation, then this curve is indeed starting from here. Okay, so at that particular point, it has some radius r at start. And then at that point right here, it is at some angle theta 1. So at theta 1, some angle theta 1, we are at that point on this polar curve. And so now, if anyone study with me, I also point out that any polar curve is a graph of a polar equation, is a graph that comes out from a polar equation. So for our study here, we're mostly going to focus on the kind of curve where the equation is in the form of a function. So r is a function of theta. Okay, so you gotta nail this down and take note on that for me. For our level here, we are mostly going to focus on the kind of polar curve where it is already expressed as r as a function in terms of theta. Okay, and so now back to what I was in the middle of saying. So this polar curve, okay, we can think about this point right here is a starting point where theta is some small angle theta, or is some angle theta 1. And then as we increase the rotation, okay, and so you can see that I'm drawing this positive direction right here, this positive, the rotation indication right here. And then we arrive and we stop at another angle right here. So this is angle theta 2 right there. So we make a rotation. Okay, we make a rotation and then we stop right here. That angle theta 2 will arrive at another radius value. But now how do I see the area? The area is the amount of shaded in this fan shape right here. Okay, the shape looks like a kind of like a Chinese fan shape right there. And that's the area we're looking for. That's the area we're attempting to calculate, okay, in polar coordinates. Okay, so it's not the straight area. It's not the straight area that we're drawing like we used to know back in rectangular coordinates. But now in polar coordinates, everything is measured in terms of how much angle of rotation. And so in a positive rotation, then the curve goes that way. So start now would have to be here, okay, and end would have to be here in the positive rotation of the circle, okay, of the angle. All right, so in that way, the area again is the amount shaded inside between the angle change from theta 1 to theta 2, right there. Okay, and so that's the idea. And so in that way, allow me to show that picture on Desmos, okay, on my favorite graphing device right there with on the web browser, so that it gives a better picture of that. Okay, so all right, so here on my browser with the graphing calculator on Desmos right here. So this is that piece of curve that I try to make a close enough replication on the board earlier. And now with this piece of curve right here, see, angle change can be from this angle theta, whatever that's small here. This is right now it's not the time to know precisely how big is that theta, but theta can be changing from whatever this is to some other theta being larger. And so now let me show the shading with all the handles so that it can show. Okay, all right, so this is the ending theta. So the pole is right here, the ending theta is right there, and the starting theta is here. So now as I show the picture, it will become clear. All right, so this is the picture over here. So when angle theta this is theta 1, this is amount of theta, and then this bigger angle is theta 2 right here. And so the change from theta 1 to theta 2, that's how we get the amount of area shaded inside of this polar curve, okay, this polar curve, and then between the angle change from theta 1 to theta 2. And that's the kind of problem that we're doing. Okay, and so again, just like I said, this shape right here that we're calculating is looking like a Chinese fan, the shape of a Chinese fan right there. All right, so let me do a quick demo, a quick illustration right here. But all right, so from that theta 1, okay, and now we're gonna make a rotation so you can observe the rotation of this handle on my graphing device. So now I'm gonna be rotating, okay, and we don't have to rotate the whole complete rotation. It's just some partial rotation that's enough to create some area on this particular polar curve. And right now it's not the time yet to worry about what polar curve this green curve is. All right, and so that's hopefully enough for an illustration of what we are about to do in terms of finding area. But those areas are expressed in terms of in polar coordinates. All right, and so now let's get even further. And so at this point, how can I see to apply? How can I see the application of calculus in here? So anytime we're finding area, it doesn't matter if it's in rectangular coordinates or in polar coordinates. Finding an area is accumulation of little areas. You have seen this idea when we were doing applying calculus into finding areas of those shapes that are expressed that were represented in polar coordinates. I mean in rectangular coordinates. So now when we are in polar coordinates, it's the same fundamental. Anytime we're finding area, we're accumulating little areas. Okay, we're accumulating little areas, and so now how do I see the little areas here? This picture of mine is already kind of drawing that. We're gonna break the whole area of this, shape like a Chinese fan shape right here. Okay, we're gonna break that into infinitely many little sectors. Okay, so I had to erase, but then to redraw, see, we break them into infinitely many of those little, we call this a sector. So each one of these little sectors really is just a small change in the angle theta, very small change. Okay, so just in between these two little radius right here, just in between that, we have a little sector. Just in between that. in between any of these two, we have a little sector. There's an area. So in any of these sectors, there's an area. And we're accumulating. We're summing up all of those little areas according to the rotation from the small angle to the large angle. Okay, so we're accumulating all of the little sector areas, and that's how we get the total area inside of this big overall sector. Okay, and so now we need to review a little bit about how we can calculate, and then the idea now is that when we need to accumulate in the end, we need to accumulate infinitely many of these little sectors. So when you draw these sectors small enough, infinitesimally small enough, then, I mean, of course, right now each radius here is a function depending on how far theta is. But then when you draw your sector small enough, then any two adjacent radii would be just nearly the same. Okay, to the point that it's going to be just infinite. It's going to be just one value. And so now, allow me to briefly remind about the concept. And so that concept I was saying, we're accumulating all the area of the little sectors. So, okay, so now I'm going to say to get the sectors areas. Okay. So we have a lot of sectors area. We're accumulating all of those. An integral sign, an integral is accumulation. And so here we're accumulating all of the little sectors areas from a start to an end. That's how we're doing it. That's the fundamental that we're doing here. All right. And so, and you can, and later on, I already had that in a picture earlier about the start and the end of our accumulation right here. We will get a little further into that as well. Okay, but for now, let's get back to the picture and understand a little more. So now, let's think about how we can find the area on each of these little sectors. Okay, so how do we find the area in each of those little sectors? Let's say you have a very small sectors. Your pole is here at that origin. Okay, and then let's say we have a sector this small. We have a sector that small, and so this is radius 1, comma, or theta 1. This sector is that long with having radius as large as r1, and this other sector here is radius r2 at angle theta r2. So between angle theta r1, between angle theta 1 and theta 2, there's a change in theta. There's a change in theta. So right now I'm drawing a delta theta. A delta theta, a small noticeable change in theta. A change from theta 1 to theta 2, from small rotation to larger rotation. Okay? And then in that way, here's how I'm seeing. And as I said earlier, assuming that the change in theta is small enough so that there's no much difference, or the difference between R2 and R1 here is neglectable to the point that it's just one R value. Okay, because just think about when this change in theta is small enough, then this is almost perfectly fit on a circle right there, a circle center at the origin 0, 0. And so the sector here, even though we're trying to describe that sector, is an extracted sector out of this. So of course it's not exactly equal, but like I said, it's close enough so that we can assume it's close enough so that we can start out by thinking about these are the two equal radius right there. So an area of a sector, a sector's area, okay, is according to fundamental geometry, or just basic geometry, then it's a 1/2 times how much radius square times, and I shouldn't need to put that the radius in the parentheses, it's taking more space. So it's square of the radius. And right now, again, like what I said, I was assuming that these are close enough to that sector on an actual circle. that's center or seated at the origin, at the pole right there. And so R2 and R1, in other words, is approximately the same with that common R, common radius on that circle. Okay? And so now, and we multiply with how much change in theta angle. That's how we can calculate the area of any small sector, of any sector actually. All right, and then the smaller each sector is, the better approximate that is, because after we accumulate, we're going to have a better approximate of the whole big sector over here. All right, so that's the idea right there. That's the idea of what we're doing. And so now, 1/2 r squared times delta theta. 1/2 r squared times delta theta. And then that's the area of one sector. And now we're accumulating. So now I'm going to swing to the other side. And before I swing to the other side, also think about it. As we try to fit more little sectors in here, fit more little sectors so that we can accumulate and get a better approximate from small angle to larger angle. Then as we keep increasing more sectors and more sectors in the same big sector here, but we try to fit more little sectors, then that delta change, that delta theta right here, the change in theta becomes so small and so small to the point that it becomes infinitesimally small. And so eventually we're going to refer to this as a 1/2 r squared, and it really makes no difference anymore about R1 and R2. So R1 and R2 can become just literally some R value at some angle theta, but multiply with the infinitesimally small change in theta, d theta. Okay, so everything here I'm doing here is I'm speaking on behalf of one infinitesimally small sector area. Okay, and now over in this picture, so we already expressed that sector's areas. Each one of those is a, well, now allow me to use the next line down. Each one of those is, of the sector areas, is a 1/2 r squared d theta. 1/2 r squared d theta. And then, how do we start? I mean, what's the start of our accumulation and where's the end of our accumulation? And so, now back on this big picture, if this is our main target of the area that we're trying to find out how big that is, then it changes starting from theta 1 and ending at this is right here is theta 2 is the end of our the theta change that create this overall shape that's like a Chinese fan like that. And so in that way, the start is from theta equals 1, theta 1, and it's ending at theta 2. So it's not theta equals 1, but it starts at theta 1 and it's ending at theta 2. That's our accumulation. Okay, and so now the start to the end is from theta 1 to theta 2. And this is how we can now, so that's area. Okay, and that's the same as the area of any sector. Okay, it's going to be using that formula. And this is actually one formula that really works anywhere. Okay, and so now with all that understanding right here, we are ready to get started into one example. So let's start out with our first example here. All right, so now I'm turning over to my lecture note on the computer screen here, and let's read into our example 1 right here. So example 1 now it's commonly saying that find the area of the region bounded by apologize for my apology for the little misspelled right here, but it's find the area of the region that's bounded by the given polar curve. So this is the polar curve. So here we are having, this is the first problem in our example 1, so I call that part A. So in part A, it gives us a polar curve, r equals 1 plus sine theta. And then we want to find the area of the region bounded by this curve on that interval from 0 to pi over 2. Okay, and so now let's look over to my graphing calculator with decimals right here on the computer screen, and let's first look at the curve itself. Let's first look at the polar curve. So now we have technologies all over. You can either use your standard TI calculator, or you can use you can also use decimals and quickly type out r equals 1 plus sine theta, and it will give you the following graph. So here's the graph for the polar curve, 1 plus sine theta. Okay, and so now with the graph here, allow me to start showing the shading. So in a zoom version, okay, now according to the requirements, we want to make the shading in between theta equals 0 and theta equals pi over 2. So right now, if you're looking at my handle right here, then this is indicating right here angle theta equals 0 over here. And now I'm going to change to angle, I'm going to change from theta equals 0 to theta equals pi over 2. And so this is how it looks. And so the shading comes along with that. Okay, so as I'm making my rotation, you can see that there's more shaded, and there's more shading area being created. Okay, so now I stopped at that destination of being at pi over 2. So the rotation will always going to go positive direction. Okay, and so in the positive direction there, we're going to start recognizing where the small angle is, where's the starting angle, and then changing to wherever that is. Okay, and so now that is the picture. Okay, so this is the shaded area between, in this curve here, we're not calculating the area of the whole curve, of the entire full curve, but we're calculating the area just in that part where it's changing from theta equals 0 to theta equals pi over 2. And that's how it happens like that. Okay, and so in that way, what we need to recognize is that our curve has already been expressed as a function. Okay, so r is 1 plus sine of theta. So just like what I was saying earlier, for our level of learning about polar coordinates right here, especially finding areas in polar coordinates, let's focus, and there are still more advanced problems out there waiting for you guys, for any one of you learning calculus. After beyond your calculus level, there are still other advanced and more complicated polar curves out there that waiting for any of us. And I still face challenge with those more advanced one as well, more complicated one as well. But so here in our particular lecture here, let's focus on those curves where r has already been expressed as a function of theta. Okay, and so that's what we already had. R is a polar, we have a polar curve here. R is a function in terms of theta. So theta is the independence variable. The angle is the independence variable, and then r, the radius, is the dependence variable. Okay, and so in that way, r equals 1 plus sine theta. And we know that it was given that we're finding the area that's where angle changes from 0 to pi over 2. So this is perfectly our start. And this is our end. Okay, that's our end. See, we always go from small to large and in a positive rotation. And so in that way, start has to be 0 and ending has to be at theta equals pi over 2. And so now all of a sudden we are ready for setting up that integral, the setup like that. So each little sector, okay, or a sector's area is going to be 1/2. That's times a radius square times the changing angle. 1/2 times the radius square times the changing angle. This is the formula we pick up from the elementary geometry. Okay, and so that means it's going to be 1/2 times, in our particular problem here, radius is expressed as a function in terms of theta. And so 1 plus sine of theta all squared and times d theta. Okay, and so that means now we are accumulating. We're putting that in an integral setup right here. So now we are ready for accumulating. So the actual area is going to be, it's an integral. It's accumulation of all of these little areas, little sectors areas. So 1/2 times 1 plus sine theta all square d theta. So it's accumulation of all of these. And now let's take a quick pause to make sure things are going consistent. And I'm really trying to make everything align with how I have taught about calculus the whole time. And in case, and for anyone who has been studying with me throughout the beginning of our calculus 2 quarter up until this point right here, I have always been explaining, and anytime I'm teaching about calculus, and especially integral calculus, I always want to double check and to confirm that the function here has the variable that is consistent with the d expression. So the d expression here is a d theta. So our function here, yes, it's a function in terms of theta. And that's why, like I said, it seems like a rule at start that we are focused. We mostly focus on those on those curves where it's expressing r as a function of theta, but that's the way it has to eventually be anyway. Okay, because even if it's given as just some general polar equation right there, eventually we have to find our way to express r as a function of theta, because that's how we can make our integral, our function in the integral, consistent with the d expression here. Okay, and so now that's more than half of the integral setup already. Let's just now put in start and end of the accumulation. Okay, so again, in what I have here on the board, the accumulation here starts at angle theta 1 equals 0 and angle theta 2 at pi over 2. So now I'm ready for filling that in. We're changing from theta equals 0 to theta equals pi over 2. And that's our setup for the integral. So allow me to rewrite that so that it can kind of be a little stand out right here. But it's an integral from 0 to pi over 2. And our function is it's a 1/2 times 1 plus sine theta all square d theta. And this is an integral that's ready to be evaluated. Okay, so now at this point, once we start setting up our integral and that, allow me to say another thing right here. So usually if this is my course, I'm teaching my students, then this material is taught after you have seen enough, and especially after you have seen enough some of the techniques in taking the antiderivative and taking integrals. Okay, because as I said, eventually we're going to have to use the fundamental theorem of calculus to get this integral evaluated and then come up with a final answer. So the step where we find the antiderivative is the step where it requires my students to learn about some advanced enough integral technique like that. So I highly recommend, this is only a highly recommendation right here, and especially for my students, and then I believe you will be arriving at this video lesson when you already have seen enough integral techniques right here. This particular technique I highly recommend to know is that it's the technique how to find the antiderivative on trig functions or trig integrals. That's the highlighted technique that's required for this problem right here. Okay, and so let's now go ahead and get started into the problem right there. All right, so that integral from the other board right there is, we can rewrite that as a 1/2 times an integral from 0 to pi over 2. Okay, and now I am going to FOIL out that square. That square earlier, it was 1 plus sine of theta all squared with d theta. So now I'm going to think of this as a 1 plus sine theta times 1 plus sine theta. Two identical factors of 1 plus sine theta multiplied together. And so by doing that, I am going to end up with the next integral here as being a 1/2. And I can pull that 1/2 in front simply because the 1/2 was just a coefficient, okay, from the earlier step. It stood here from the step in the other board, and now I can pull it out front. So that 1/2 remains in front as a coefficient the whole time. So now it's going to go 0 to pi over 2. All right, and so now I'm going to FOIL that out and become 1 plus, and then this is 2 sine theta plus, and I realize I need even more space, so 1 plus 2 sine theta plus sine square theta, okay, and then there's a d theta. All right, so that's the integral. And so in the next step, it's going to be, we can think of that as 3 separate integrals. One of them is a 1/2 with the integral from 0 to pi over 2 on d theta, plus the next one here is going to be a 1/2 times the integral from 0 to pi over 2, okay, on 2 sine theta d theta. And the last integral here is a 1/2 times the integral from 0 to pi over 2 times sine square of theta d theta. Okay, and so this one here is easy, that one here is easy. And so that can be, this one here can be just simply a 1/2 theta as an antiderivative. Okay, and then we're going to eventually use the fundamental theorem of calculus to evaluate that from 0 to pi over 2. Okay, and I'm going to hold on to that. And plus, now this one here, we can cancel the 2 with that 1/2 right here, so that leaves me, and so in the end, taking the antiderivative of sine right here, it gives me just a minus cosine theta. Okay, and then from 0 to pi over 2. Okay, and then plus with the 1/2. Now, this one here requires it's even a little more strict in terms of the requirements about we have to know how to integrate, how to find the antiderivative on a sine square right there. Okay, and so after recalling about the techniques we have learned from our past understanding about the techniques, and there are quite a few different ways how to find the antiderivative on that. So allow me just to get straight into the final antiderivative of this. So it's a 1/2, but then the antiderivative of sine square is going to be a 1/2 theta, okay, minus a 1/4 times, it should be a 1/2 times sine theta cosine theta. Okay, that's the antiderivative for that. And then we are going to evaluate this from 0 to pi over 2 again. Okay, and notice that this 1/2 times sine theta cosine theta right here can be, including with the 1/2, can be all written together using a trick identity right here. Then this can be re-expressed as a 1/4 times sine of 2 theta. You are always welcome to pause the video, use your trick identity to expand this out and see if you can verify that this will equal to 1/2 times sine theta times cosine theta. And with your understanding in trigonometry, it should be enough for you. To see that 1/2 times sine theta cosine theta will equal exactly 1/4 sine of 2 theta. Okay, so I'm leaving that for students of mine and viewers to verify that. But so in that reason, allow me to, instead of writing the lengthy form, I'm going to write this as 1/4 times sine of 2 theta. Okay, but now we are ready for evaluating. And so notice, even though I broke it down into 2 separate integrals, but in the end they are just one integral at start. Okay, and then 3 separate terms, but in the end they are still just that same integration interval. And so allow me to regroup them again so that we can see a little bit better use with that. And then, by the way, I could have also distribute that 1/2 factor. So now in the end, so here I'm looking at 3/4 theta minus cosine theta. Now that 3/4 came out because I added this 1/2 theta with the 1/4 theta right there. That's how I ended up with the 3/4 theta minus the cosine theta, and then minus that 1/8, so minus 1/8 sine of 2 theta. Okay, and now at this step right here, we are ready for. All right, at this step right here, we are ready. This is our final antiderivative of the 3 terms together. I tear it down into 3 separate terms, 3 separate integrals, so that it gets our work done more easily, and then so that we can focus on that particular integral. But then now in the end, it's just this one antiderivative of all these 3 terms like that. Okay, and so now here is where we are ready to substitute in our 2 the upper bound and the lower bound, the upper limits and the lower limits of our the integral problem into this antiderivative and start evaluating out. Okay, so I am going to move into this board, okay, and get my answer calculated. So that is going to give me 3/4 times pi over 2. This is how I substitute in that upper limit, and then minus cosine of pi over 2, okay, minus 1/8 times sine of 2 times pi over 2. All right, so all that here is the antiderivative evaluated at theta equals pi over 2. And then the next one here I'm going to subtract, and then here I'm looking at 3/4 times 0, okay, minus, and here is a cosine of 0 minus 1/8 times sine of 2 times 0. All right, and so this term is a 0. That term here is also a 0 eventually, okay, because the sine of 2 times pi over 2 is a pi, so sine of pi is a 0. So 1/8 times 0, just 0, that's a 0. Now this is going to also be this is a 0, okay, that go to 0, this is go to 1. All right, so, and then that's go to 0. So we have a lot of cancellation to the point that I don't even need to swing by my my calculator at the computer station to get a final numerical answer right here. So I see here 3/4 times pi over 2, that gives me 3 pi over 8, okay, and that's a 0, that's a 0, and that's a 0, minus 1, okay, that is our final answer. Or here we can make common denominator and put that into one fraction, so it's going to be a 3 pi minus 8 over 8, okay, that is our final answer, or you can stop at your final answer right there, okay. But that's how we can do the calculation. That's how we can calculate the area of the area as described in the problem. It's the area on this curve here being the curve 1 plus sine theta. Okay, and then in between the angle change from between that sectors where the angle changes from theta equals 0 to theta equals pi over 2, and that's how big this area is. All right, so let's now look at another problem right here in the same example. So we're still in example 1. Let's find the area of the region that's bounded by the given polar curve. So the polar curve we're given this time is r equals cosine theta. And then the interval given here is from pi over 4. The angle theta changes from pi over 4 to pi over 2. And that's how we created our sector here. And so again, just like how I was describing earlier, the polar curve we're looking at here is already expressed as a function r in terms of theta. Okay. All right, so now back on the board right here. The curve we have is expressed as r equals cosine theta. So the independence variable is theta, or as the radius is the dependence variable. And then with this polar curve, we are going to calculate the area that happens where we have angle change from pi over 4 to pi over 2. All right, so now let's have a picture of that. Let's have a picture of this polar curve as well as the area that's created by angle change from pi over 4 to pi over 2. Let's see how it happens. All right, so here we are on Desmos, my favorite graphing calculator. Okay, and here's our polar curve for r equals cosine of theta. This is the polar curve. Okay, and again, I am sure that I have had other or earlier video lessons about how we can graph something like this, either using technology or we can do that by plotting the points through the table of values. But now here, this is our technology already gave us this curve right here being the curve r equals cosine theta. So let's look at the shading that comes out from pi equals, from the theta equals pi over 4 to theta equals pi over 2. All right, so now here's the start of our angle. So this is right now angle theta is at pi over 4. This is that line with the little handle in solid the line right here. Okay, and so with this handle, it's currently giving me this angle theta. So at start, angle theta 1 is at pi over 4. This is what it is. And now we're going to change that to pi over 2. So pi over 2 is where this handle is going to land right at that vertical axis. Okay, so let's now observe the change. Okay, so let's see the shaded area right here. So from pi over 4 to pi over 2, so as our handle is getting closer and closer to pi over 2 right here, then you can see that the amount of area keep changing and keep getting close to. All right, so now let me keep increasing it. All right, let me keep increasing it. So now here we are right at pi over 2. Okay, so now when we are changing from pi, as we change from pi over 4 to pi over 2, we have created this amount of area inside it, bounded inside the curve, and between the two angle changes right there. All right, and so in that way, so now we have after having a clear picture, let's look over to the board and let's really get settled in with that. So again, this is another quite straightforward problem right here. You have the curve given, and we can see that with the graph, and we do a little the angle change demonstration right there so that we can see what the area is. Okay, and so the start makes sense to be here. Okay, and the end that's the end of our accumulation. So now I'm going to introduce a sector. So the area we always going to start out with, and it's always a good habit to start out with finding the area of one little thing, and then we're going to set up the integral as accumulation of all the little areas. So a sector's area is calculated by 1/2 times r square times d theta. And then in that way, for each area in our curtain, according to our curtain polar curve, then we're looking at 1/2 times the radius here is expressed as a function of theta. So cosine of theta r squared. Okay, with the d theta. Or another way of writing this is just simply a 1/2 cosine square theta in traditional trigonometry expression right there. So we write cosine square theta instead of cosine of theta r squared. It's the same thing, but this is a little more convenient way of writing it. But that's the area for one sector, or in the way how I'm saying, it's a sector's area. So now to find the actual total area, okay, the total amount of area is going to be the accumulation of all of those little sectors areas from the start here being at pi over 4, and we ending our accumulation at angle pi over 2. So here we're looking at 1/2 times cosine of theta, or 1/2 times cosine square theta, d theta. And that's our successful integral setup. Okay, and so now in order to move on to the next step, at this point we are ready to apply the fundamental theorem of calculus, the second part, to evaluate this integral. And this is where I further emphasize that it is highly recommended to understand and to view this lecture after you have learned some of the techniques in finding the integral for trig functions, or more specifically how to handle trig integrals, because this function here is a trig function right here, and it's a square on a trig function. But it shouldn't be a too much of a challenging one yet. Okay, so now I can see that we have a 1/2 factor here, like we can bring it out front as a coefficient. So it's a 1/2, and now multiply with the integral from pi over 4 to pi over 2 cosine square theta, d theta. Okay, and so now here we just individually need to find the antiderivative of cosine square theta with the d theta. So on my next board space right here, let me remind for anyone that the antiderivative, so cosine square of theta, d theta. The antiderivative for that is going to be a 1/2 theta plus 1/2 sine theta cosine theta. Okay, and then plus c. So you can review, at least for students who have been studying with me, you can view all the video lessons on the trig integrals techniques right here to know how I arrive at this. Okay, and then now we can rewrite this. I mean, the 1/2 times sine theta cosine theta, we can use a trig identity to rewrite that as a 1/4 sine of 2 theta. Okay, and so you can always pause the video and use your trig identity understanding to show, to prove to yourself, to convince yourself that these two are equal expression. Okay, so in that way, now I'm going to write it as a plus 1/4 sine of 2 theta. All right, so we have all the elements that we need in order to start out with that fundamental theorem of calculus. So our actual problem here is 1/2. Okay, so the area equals 1/2 the integral from pi over 4 to pi over 2 cosine squared theta d theta. But that now is 1/2 times the antiderivative of cosine squared is here. Remind it on the board. So it's a 1/2, another 1/2 theta plus 1/4 sine of 2 theta. Okay. And then when we're using the antiderivative in the fundamental theorem of calculus, we don't need to write the plus c. Just another reminder right there. And here we are evaluating from from pi over 4 to pi over 2 right there. All right, so there we have, now we are ready for evaluating. So I'm now going to, and it's better that we distribute that 1/2 right there. So here one more step. I'm going to write it as a 1/4 theta plus 1/8 times sine of 2 theta. Okay, and then that's ready for evaluating from pi over 4 to pi over 2. And so now I'm looking at 1/4 times pi over 2 plus 1/8 times sine of 2 times pi over 2. All right. So that's the antiderivative evaluated at the pi over 2, the upper limits. And now I'm going to subtract. Okay, I'm going to subtract the antiderivative 1/4, but evaluated at the bottom limit right there, the lower limit, plus 1/2. I mean 1/8 times sine of 2 times pi over 4. Okay. All right. And so that is going to be our evaluation step right here. And I ran short of board space, so allow me to jump the line just like that. All right. So now I'm going to swing over to this board to complete my calculation. All right. So from that particular term right here, okay, with that term right here, 1/4 times the pi over 2 is going to give me a pi over 8, right? And then this is going to be a 0. All right, so now I am going to write that as a, so from the first group of brackets right here, we're looking at pi over 8, okay, plus 1/8 times sine of pi, okay, which will easily become a 0. And then I'm going to subtract, so I'll just move in careful steps right there. All right, and so now with that part right here, okay, we're looking at so 1/4 times the pi over 4 is a pi over 16, okay? And then I still keep things in the brackets right now, plus a 1/8 times sine of, now 2 times pi over 4 is going to be a pi over 2, okay? Which will eventually, this is going to be a 1, this is a 0, okay? So now I'm ready for my next step right here. It's a pi over 8, we don't need to add that terms, minus pi over 16, okay? Plus a 1/8 times a 1. Okay, so all together this is going to be, So now I'm going to make common denominator for those two and add those like terms right there. Okay, and so that is going to be a pi over 16, positive pi over 16 plus a 1/8. So that's one way you can express your final answer. Okay, and then we can also make common denominator and put this into one fraction. So here I'm looking at pi plus 2 over 16. All right, so two different forms how we express our final answer. But that is how much area of this shape right here, okay, of this area bounded by the curve. This is r equal cosine theta, and then but the area is bounded by angle change from pi over 4 to pi over 2. So let me once again do that demonstration. So pi over 4 to pi over 2. All right, so that's the amount of area created by that angle change right there. All right, and that's how that problem is done. That kind of problem is done.